Assalamualaikum and hi everyone. We are students from University Malaya, and in this video, we will be sharing the outcome of our analysis of the crystal structure of Aurum based on the experimental data provided.
We plotted the XRD graph of the Aurum sample using Origin Pro. The graph showed 4 distinct peaks. Using Bragg's law and assuming a cubic structure, we calculated sin theta and compared the values to Miller index squared 3, 4, 8, and 11. The ratio sin squared theta of S was consistent to 0.036, indicating a constant lattice parameter. This pattern matched a face-centered cubic structure. Therefore, the corresponding planes are 111, 200, 220, and 311, which confirm that our Aurum sample is FCC structure.
Now, let's move on to the comparison between the experimental X-ray diffraction data of Aurum and the standard data retrieved from the material project database. On the top right, we can see the experimental data obtained from our SRD analysis. The major peaks appear at 2 theta values of 38.1 degree, 44 degree, 65.3 degree, and 77.2 degree, which correspond to the 111, 200, 220, and 311 planes respectively. Meanwhile, the bottom right table shows the standard diffraction data for Aurum from the material project. The peak also occur at similar plane 111, 200, 220, and 311 with slightly different 2 theta values. This slight shift can be due to experimental condition or sample purity. Now let's take a look at how we determine the lattice space D for each plane. We use Bragg's law and we rearrange the formula to this equation where the wavelength is the X-ray wavelength, which is CUK alpha radiation, lambda equal to 1.5406 Armstrong. After calculating the D spacing, we use the formula for cubic crystal to find the lattice constant A equal to D times H squared plus K squared plus L squared. We follow this method for all planes, and the average lattice constant from the experimental data is approximately 4.0834 Armstrong. Meanwhile, the reference data gives an average of 4.1718 Armstrong. This shows a minor deviation, which is within an acceptable range for most practical purposes. Overall, the XRD result confirms that the sample is crystalline gold with peak position and calculated lattice constant, showing good agreement with the reference FCC structure of Aurum.
Crystal structure of Aurum. The primitive lattice of Aurum in real space is rhombohedral, while in reciprocal space is rhombohedron. The first brilliant zone is shaped like a truncated octahedron. Aurum belongs to the cubic crystal system with an FCC Bravais lattice. Each unit cell has 4 atoms with an atomic cracking factor 0.74. The structure factor is equal to 4F when HKL are all even or all odd, and equal to 0 when HKL are mixed with even and odd. So the allowed reflection are at plane 111, 200, 220, 311. The strongest intensity was at 111 plane, showing its preferred orientation. Our experiment peaks match these planes.
Now, let's look at the nature of metallic bonding in gold for chemical bonding. Gold exhibit metallic bonding. This is a type of bonding where valence electrons, especially from the SIF orbital, are not bound to any single atom. Instead, they are delocalized and free to move throughout the entire crystal lattice. This creates that we call a sea of electrons or an electron cloud. These clouds surround the positively charged gold ion and hold the structure together through electrostatic attraction. Moreover, gold crystallizes in a face-centered cubic structure. This geometry is important because it gives atom a coordination number of 12, meaning every gold atom is surrounded by 12 neighbors. This high coordination leads to significant overlap of atomic orbital, particularly the 6s and 5p orbital. The result is stronger bonding between atoms and tighter atomic packing. This dense packing increases the overlap of the electron cloud and enhances cohesive force. As a result, gold exhibits very high electrical and thermal conductivity. Speaking of properties that connect bonding with real-world behavior, gold is an excellent conductor of electricity than silver. Why? Because it relocalized electron can move freely and easily carry electrical current. The same electron also carry heat very efficiently, which is why gold also has high thermal conductivity. This metallic bonding also allows layers of atoms to slide over each other smoothly, giving gold its famous docility and malleability. And of course, gold bright luster and reflectivity. This comes from how freely each electron can interact with and reflect light wave. Finally, for relativistic effect, in gold, the 6s orbital is contracted due to relativistic contraction. That means the electrons in this orbital are pulled closer to the nucleus and have lower energy. This contraction enhances as the orbital hybridization, which further strengthens the metallic bonding. But interestingly, this effect also explains why gold has a yellowish color. Due to relativistic effect, gold absorbs blue light in the visible spectrum and the reflected light appears yellow. That's why gold is so visually distinct among metals. Thus, gold unique metallic bonding, FCC structure, and relativity effect all contribute to its remarkable strength, conductivity, malleability, and appearance. And that's why make gold not just beautiful, but also incredibly useful in electronic, jewelry, and technology.
The first graph shows the phonon dispersion of gold. Since gold is FCC structure and is monoatomic, there are only 3 acoustic phonon branches, 1 longitudinal acoustic and 2 transverse acoustic modes due to perpendicular vibration. It have no optical modes because gold has only 1 atom per unit cell. The phonon frequencies are low due to heavy atomic mass of gold and weak metallic bonding. The second graph shows the band structure and density of states of Aurum. On the left, Fermi level is at 0 electron volt, represented by white horizontal line. Multiple bands cross the Fermi level, especially around L and X points, indicated no band gap since gold is metal. With the presence of free electron, it enables excellent electrical conductivity. On the right-hand side, dose is continuous at the Fermi level, which confirms the metallic behavior.